In today's video, we're going to look at the second half of section 6.4, which looks at independence of events. I'm going to give you a couple different scenarios here to show you what independence means, and then we're going to look at it mathematically. Let's say that I have two events. I'm going to roll a die twice, okay? My event F is going to be that the first roll is a 5. Okay? And my event E is going to be that the second roll is a 1. We know intuitively here that regardless of what we get on the first roll, it's not going to affect what we get on that second roll of the die, telling me that these two events are actually independent of one another. So therefore, I know However, let's say I now take the situation where I have an event F, which is looking at a deck of cards, and I have that the first card is red, and then my event E is that the second card is black. And I'm doing this without replacement. Okay. Now, what happens when I take out my first card will affect what happens when I take out my second card, because it's going to affect the overall number of cards in the deck, and therefore my chances of drawing either red or black is going to change for the second time that I pull a card out. So E and F are not independent in this case. So intuitively, we can see what independence means here when we look at events. What does this mean mathematically? Well, it means that E and F are independent provided that we have that the probability of the intersection of E and F occurring is equal to the probability of E multiplied by the probability of F happening. So the probability of the intersection of events is just going to be the multiplication of the probability of the event E and the probability of the event F. Where does this come from? If we go back to our product rule, remember that in our product rule, when we looked at conditional probabilities, we know that this was the formula that we would use. Okay, the probability of the intersection of E and F is equal to the probability of the event E happening, given that F is going to happen or has happened, multiplied by the probability of F. Now, when we look at this and we look at that conditional probability, we are looking at the probability of E happening, given that F is going to happen or has happened. Well, if the events are independent, it doesn't matter if F has happened or not. The probability of E, given that F has happened, is just going to be the probability of E. Because if E and F are independent, it's not going to matter if F's happened or not. We're just looking at the event E because they are independent of one another. So the probability of E, given that F has happened, is just going to be the probability that E happens, multiplied by the probability of F, and that's where this comes from. So therefore, if E and F are independent events, and I'm also going to put the stipulation here where the probability of E doesn't equal 0 and the probability of F doesn't equal 0, just so that nothing here cancels out and equals 0. So both E and F can happen, okay? They're not going to happen. There's not a 0 probability. Then the probability of E happening, given that F has happened, is going to equal the probability of E, because it doesn't matter whether F has happened or not. They're independent of one another. So it's just going to be the probability of E. And the probability of F happening, given that E has happened, is just going to be the probability of F. Because again, it doesn't matter if E's happened or not. If F and E are independent, that's just going to be the probability of F occurring. So the first example I'm going to look at is going back to where I had these events E and F. So E is the second roll and F is the first roll. So E is the event that we have a 1 on the second roll of a die, and F is going to be the event that the first roll is a 5. I want to see if these events are independent or not. Okay, we've already looked at this intuitively and said yes they are, because it doesn't matter what happens on the first roll, it's not going to affect what happens on the second roll. Okay. So I'm going to show that the probability of E, given that F has happened, is equal to the probability of E. Now I already know that the probability of E is equal to 1 over 6. Okay, I have a 1 over 6 chance of rolling a 1. Okay, regardless of the fact that it's my second roll, okay, it doesn't matter, we know all of that. I know that the probability of rolling a 1 on a die is 1 over 6. I want to show that the probability of E, given F has happened, is also 1 over 6. What I would do here is go back to my conditional probability formula. So the probability of E, given F, is equal to the probability of E intersect F over the probability of F. Now, I know that all of my outcomes here are equally likely. So I know that the probability of E intersect F is going to be the number of outcomes in E intersect F over my total number of outcomes. And then my probability of F is going to be the number of outcomes in F divided by my total number of outcomes. The total number of outcomes cancel one another out, and I get this fraction here. I need to figure out how many outcomes are in that overlap, and I also need to figure out my number of outcomes in F. Let's look at what outcomes are in each one. Okay. For E, I'm saying that the second roll is 1. That means I can have anything for my first roll. So I have the outcomes 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1. Okay, all of those, the second roll is a 1. First roll, 1 through 6. It doesn't matter what the first roll is. For F, okay, I'm saying that my event F is that the first roll is a 5. So my second roll can be anything. So my first roll is a 5. So I get 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. Okay. If we look at this, the only outcome that these two have in common is 5, 1. So that tells me that the number of outcomes that are in E intersect F is just 1. And my number of outcomes in F is 6. So when I look at the probability of E, given that F has happened, going back to my conditional probability formula, I simplified this down to the number of events in that intersection divided by the number of events in F, which would just be 1 over 6, which we've already said is the probability of E. Therefore, E and F are independent. You could also do this the other way around. It makes more sense this way around because you are looking at the first and then the second roll. So the probability of what happens on the second roll, given that we've already got something on the first roll. You could also show that the probability of F, given that E has happened, equals the probability of F. You're assuming, therefore, that the event E is going to happen. It hasn't happened yet because you are looking at E being the second roll. So you could also prove it that way around. But I have proved that the probability of E, given that F has happened, is equal to the probability of E. So you can prove it either way around. The other example that I want to look at here is where we have said that E is the event that the second card is black, and F is the event that the first card is red. Again, we've already shown that these two are not independent. We know that because whatever I pull out on my first card is going to affect the number of cards left in the deck. So if I pull one card out, I'm left with 51 cards. So that's going to affect my probability of what I get on my second draw of a card. Okay. Let's look at this to show mathematically that these are not independent. Probability of E. Okay. I'm ignoring the fact of what's happening with F right now. I am just looking at what is the probability of E happening. Okay. The probability that a card is black is 1/2. Now I want to look at what's the probability of E happening given that F has happened. So I know that the probability of drawing a black card is 1/2. Now what's the probability that that card is black given that I know that my first card was red? Okay. Well, if my first card is red, I'm one card down, so I'm left with 51 cards, but I still have all 26 black cards in a deck. I'm down to 25 red cards after that, but I still have 26 black cards in a deck. So my probability of E happening, given that I've drawn a red on my first draw, I'm down to 51 cards, but I still have all 26 black. So 26 out of 51 is my probability. These two don't equal one another. So therefore, E and F are not independent. You can extend this idea if you are looking at multiple different events. Okay. Going back to when we were looking at independence, we said that the probability of E intersect F, because of the probability of E given that F has happened equal the probability of E, we said that this equaled the probability of E multiplied by the probability of F. Okay. You can extend this. And you can go all the way along, let's say, to Z, okay? Depends how many events you've got. This extends to however many events are independent. So this works as long as your events are independent. So your event E could be that you roll a 5 on the first die. Your event F could be that you roll a 1 on the second die. You could keep going and say that your event Z was that on the 10th roll, you rolled a 3. Okay? Each roll of a die is independent of the one that you rolled before. Therefore, all of these events are independent. So to find the probability of the intersection of these events, probability of all of these events happening is going to equal the probabilities of each of them multiplied together. So it does extend to however many you have.